Well, good morning, everybody. We're going to start by introducing everyone. My name is Liana Vela.
I'm Adrian Lopez.
Joshua Bailey.
Isaac Moreno.
Kaden Rozaki.
Okay. And we are going to be presenting our senior design project called Scorp Bot. Oh, okay. These are basically all the topics that we're going to be going over today. But first, we are going to start with our introduction. And to start off this presentation, I thought it was best to start on what inspired us for this project. Some of us had the privilege of working at an internship over at the Texas Department of Transportation. There, we were able to witness firsthand of the maintenance work that actually went into our infrastructure, particularly in culverts. And culverts, for those of you who don't know, are channels or structures underneath bridges, driveways, and roads that prevent flooding and basically maintain the integrity of our roads. So what stuck with us was the magnitude of hard labor and intensive effort that went into actually maintaining and repairing our culverts. So it was clear to us that something needed to be done to, or at least have a better solution to fix this problem. And our problem statement. So ironically, there is a solution to repairing culverts already. That solution is using a polyurethane liner. Polyurethane liner is a material that is sprayed around the inside of the culvert and hardens over time. This basically creates a protective barrier around the culvert that prevents damage and also repairs damage that's already been done. This is a really great solution in itself. The only problem is the application process itself. Currently, the application process is done by hand. As you can see here, there's a worker that is spraying the polyurethane liner around this culvert. You can imagine there are many problems that arise with this process. One of them being the potential inconsistent coverage of the polyurethane liner, worker fatigue, and more importantly, worker safety. As you can see in these pictures, there are workers sometimes crawling inside these culverts in full PPE, which is personal protective equipment. The reason is because this material is also hazardous if it were to come in contact with your skin or if you were to breathe this in. So they have workers going into also a confined space, and not to mention that majority of these pictures were taken in the middle of the summer, in the middle of July, in the middle of the day. So you can imagine the temperatures that they also had to endure in Texas as well. Now, to gain more information on the application process, we were in contact with TxDOT, which is Texas Department of Transportation, and also companies that service TxDOT, including a company called Fuquay. Fuquay actually specializes in maintaining culverts. So both of these companies were able to give us a lot of insightful information to help further along our project. Now, with what we learned, we knew that we had to create a more efficient and safer way to repair culverts. And also create a senior design project that no one else has done before. So that was kind of where Scorp Bot was created. Scorp Bot is a rover with a robotic arm that applies the polyurethane liner by itself. So our rover single-handedly eliminates all of the problems that come with the application.
Now moving on to our objectives. So for our objectives, we wanted to implement a fully functional spraying mechanism. So being able to apply the spray liner to our culverts. We also wanted to reduce any inconsistencies by 60%. And we also wanted to see how our rover would perform under various environmental conditions and culvert sizes. Also, we wanted to refine our control algorithm and system to precisely control our robotic arm that we have. And we wanted to increase any efficiency by 100%. We wanted to improve our worker safety by minimizing their exposure to any hazardous environments by 90%. And we also wanted to reduce our labor costs by 70%. For some constraints, we are limited in culvert size from a 4x4 up to 11x11. We're also limited to a culvert length of 400 feet, and that is due to the length of our heated hose/tether. And also, OSHA guidelines do state that a single person cannot lift more than 50 pounds.
So now we'll jump into our design methodology, as well as some optimizations we've made over the past year. So here you can see this is our first two initial designs, and these were just designs that were kind of to start the design process and the optimization process. As you can see from this first design, the rover was a little bit smaller. We weren't sure quite the scale that it would need to be just yet. As you can see, there's stabilizer arms on the sides of the rover to keep it stabilized as that long spray nozzle would go out and spray the sides of the culverts. As you can see, it kind of looks like a scorpion, which is how we got our name, Scorp Bot. Now moving on to the second design here, it's a little bit bigger. We discovered that in order to spray these larger square culverts, it would require a more robust rover, but we were still struggling with getting the degrees of freedom necessary on that spray arm needed to spray those square culverts. And that brings us to our final design, which actually includes 7 degrees of freedom. This rover features a revolving base, which resembles that of an excavator. It also features the fully aluminum arm, and this arm can extend, it can articulate. It also features a spray track at which the spray nozzle rests on and moves at a speed of 0.4 feet per second. The spray nozzle is positioned 10 inches away from the sides of the culvert that it is spraying, and that whole track is approximately 3.5 feet long. This rover weighs about 180 pounds. So divide that by 4 and you get 45 pounds a person. We have 4 different lifting lugs on it. So if 4 workers were to lift this rover, that would be about 45 pounds each, which abides by that OSHA regulation that Isaac mentioned earlier, that they cannot lift over 50 pounds. Now we'll go into our detailed design portion of this report. Now this is our track system. It's approximately 4 foot in length by 3 foot in width. And this is quite large actually. And the weight is 121 pounds. And this is pretty heavy considering that the overall weight of the entire rover is 180 pounds. But as I mentioned earlier, the arm is fully aluminum. And so that means it's going to only be about 50 to 60 pounds. Now we designed this track system to be comprised of mostly steel. That way that our center of gravity and our center of mass is a little bit lower, so we can achieve all the extensions and all the angles we need to in order to spray these square culverts without having to worry about it tipping or becoming unbalanced. Now that takes us into our chassis and our motor mounting frame. So our motor mounting frame is comprised of several different steel 90-degree L brackets. This rover is driven by 2 powerful NEMA 23 stepper motors. They have a maximum of 500 RPMs. And these stepper motors have a maximum holding torque of 467.3 inch-ounce. And when you convert that to foot-pounds, it comes out to be about 36 foot-pounds when you take into consideration the 1.5 gear reduction provided by our driving sprockets, as well as the 1-to-10 gear ratio provided by our gear reducers that are coupled to the stepper motors. Now, we set the specifications for this rover to have a maximum speed of 5 feet per second. And using this maximum speed of 5 feet per second, we calculated that the maximum driving force required to actually move this rover was 3.5 foot-pounds of torque. And when you compare this to the 36 foot-pounds of torque produced by each stepper motor, it seems like a low number, and it seems like our motors are overproducing. But you have to remember that we are dragging possibly 400 feet of heated hosing and different cables, such as like power cables. So that's going to provide a lot of friction. So those overpowered motors are necessary.
So this brings us to the load-bearing plate. This plate will undergo the entire weight of the top part of the rover. It is designed using an 1/8 of an inch steel plate that is bent upwards at a 150-degree angle to counteract any bending stress that we might endure. It is then bolted to the side, the roller supports through those on the little side. There's 8 bolts, 8 number 10 bolts that would be bolted to the roller supports. That big gear you see on top is called a slew gear. That allows the top of the rover to rotate 200 degrees. And then that slew gear is then mounted to the plate using 50 bolts to the outer ring of the gear, sorry. And then this brings us to the tension system. The tension system is used to keep tension in the tracks while it's being used. It is composed of a rack and pinion gear inside of a housing. Welded to the end of the rack the rack is a bracket that holds the idler. To add tension, there is a shaft connected to the pinion gear, which you could use a wrench to drive out and then bring back in that rack, which will then add tension and then remove tension from the track. In order to hold tension, there is pins in, the pinholes inside the rack and one inside the housing unit. So whenever you reach that desired tension, you could just slide a pin in there and it will keep the tension that you want.
Alrighty, so now we're gonna go to the very top end of our arm, excuse me. So all of our arms and our components in our arms are actually custom aluminum extrusions. The material that we're using here is ASTM 6063 with a T5 heat treat. We chose that material for its wear resistance, it's lightweight, and it is cost effective. We have a track on this arm that will go back and forth. It is a V-track, and we use V-track rollers. On here, we have 2 on the top and 2 on the bottom, so it locks it in because the track can tilt and go upside down. So we need to make sure it's locked in. And we're using all metal components, so we have no items that should wear down over time. So we don't have any inconsistencies in the spray application. On the end of the track, we have our belt tensioners, and then we have a stepper motor that drives the belt in the middle. The track is pulled along by an XL size belt. And we have everything in the track balanced, so in its resting position, we don't have to worry about the track flopping around. It can lock in real nice and easy. For the Arm 2 assembly, it contains the track mounting bracket at the top and connects to Arm 1 at the bottom. This arm is also a custom extrusion. It is approximately 3 feet long and is made of a slightly different material. It is 6061-T6 aluminum. This aluminum, we got quotes for it, is approximately 10% cheaper on the material side as opposed to the other one, and we don't need quite as much wear resistance as the 6063 aluminum gave us. At the top with that bracket, we do have a stepper motor there that will help spin the track. That is one of our degrees of freedom. And then directly below that, we also have our tilt function that is operated by a 5-to-1 gear reduction gearbox. That's a 90-degree gearbox. And then the stepper motor is actually located at the bottom of the arm near the pivot for the next arm. That is to help reduce our torque required to lift the arm. Hoses for this are mounted externally near the bottom, so we have plenty of extra slack for our carriage as it moves across. So we don't have anything to worry about inside the arm. I'm trying to make sure that we don't twist any hoses or have plenty of slack so we don't have any spray carriage issues. The upper arm assembly, the Arm 1 is actually a telescoping arm. So there's 2 parts to this. There's an upper and a lower. The upper part of the arm, of course, holds Arm 2 that we just looked at. This arm is, when it is collapsed, it is approximately 3 feet long. And when it is fully extended, it is 5 foot 10 inch. It attaches onto Arm 2 by a 20-to-1 gear ratio, and the stepper motor, just like the other one, is at the bottom of this section of this arm. Wires and hoses are internal on this part of the arm to make it simpler because of the telescoping motion, and we use a wire chain inside to prevent the wires from getting caught up in any of the moving components and to help guide it as we do the telescoping action. We use a lead screw with an Acme and lead nut. The nut is on this part of the arm. And then the motor and the stabilization for that lead screw is actually on our lower assembly. The lead screw itself is approximately 3 feet long, and we spec'd it to the correct size so we don't have to worry about any lashing effects inside of the arm. I believe it was a 5/8 lead screw. We also use the exact same V rollers on these extrusions as we do on the track, so we don't have to worry about things like poly plates wearing down over time, adding slack into our system and causing inconsistencies in our spraying. This attaches to the base with a 50-to-1 gearbox, and all of this, most of this arm assembly uses the same stepper motor with the exception of the spinning function. So this entire arm has a grand total of 7 degrees of freedom, and we designed this not necessarily in the form of stress, but actually in rigidity. We wanted to eliminate as much flexing and as much ambiguity as possible for our control systems, which we will now go over.
Now we're gonna move on to our control system. Since the beginning of our project, we knew that the control system was going to be a very important part. Considering that most of us had little to no experience in robotics, we knew that it was also going to be a complex part of our project. But luckily, there are already established algorithms, principles, and theories that are in regards to robotic arms. So it was just a matter of implicating that to our project.
Now here's our control algorithm. So we decided to use Lyapunov theory, which is with adaptive control, and that just ensures the stability and performance of our robotic arm. So as you see pictured to the left, that is our algorithm that we created ourselves. Our first equation, that is our dynamical equation. X is the position. We have three thetas, theta 1, theta 2, and theta 3. And that's just because we're gonna have three angular positions based on how many linkages we have on our robotic arm. U is our controller, and V is our Lyapunov function. And all we're doing here is just deriving it to prove that it is stable. And once we're able to do that, we're able to rearrange at the end to solve for our U, which is y a hat minus ks. And that is our controller.
Okay, so continuing what from Isaac was saying, that our control law basically regulates every movement of our robotic arm. So our next step was making sure that we'd be able to simulate this algorithm. So we did use two different programs, one of them being MATLAB and the other being Simulink. Simulink is a program that actually is specifically made for simulation of the controls and algorithms. So an example of this would be in this picture right here. This is an example diagram of kind of how Simulink works. Here in this box would be where our control law goes. And then right next to that would be our lines of code that Isaac explained earlier, which is our dynamic equation. There we would actually have to find the variables of m, v, and g, which are very important to our dynamic equation. That was needed in order to have a simulation. And then everything underneath is the sensors that were provided by Simulink. So this was able to let us know if our algorithm was actually in the right direction.
So the control block, as Len was saying, this is kind of the brains of our operation. We need to be able to take this and implement it with our rover to get fully functional mechanism. And then also we have a product architecture. So for our product architecture, here on our left, it's just showing the program of our controls and how we encompass it with our rover.
Alrighty, now we're gonna go over our wonderful prototype that's sitting in front of our screen here. So we knew that we wanted to do some sort of prototype or visual aid. And originally, when we chose to do it, we wanted to 3D print it because we have a lot of custom extrusions, and that's gonna be kind of hard to try to articulate that in this fashion. We attempted to originally just take our large scale design and scale it down. However, we did run into enough issues that we realized that was not going to be a feasible option. So we had to redesign a large part of this to get it to try to be a functional prototype. Because of that, we had 3D printing issues, from printing errors to small dimensional errors. So we even actually broke a couple parts trying to assemble them because they were a little bit too fragile. So unfortunately, our model in front of us currently does not work from a physical standpoint at this time. But we do have the electronics and we do have the programming to make it work. There was just a slight issue with one of those components.
So this brings us to our budget. As you can see, there's a lot of stuff here. We first initially allocated about $10,000 for this project. And then as you see highlighted, those are our four most expensive parts of our project, which would be the DC motors, the gearboxes, the rubber tracks that would have to be custom made, as well as we allocated about $1,000 for manufacturing. And then this brought our total cost to about $7,058, which is about $3,000 under budget.
That will lead us into our next steps. So for our next steps, we wanted to improve our rover's controller system. As Liana has stated, we had really little experience with robotics within itself, so we knew that would be a challenge. Adding to that, we want to add more features and make sure that our rover is reliable. We're also working really hard to make our design better. So our focus right now is actually building our actual model rover and making sure that it's effective and ready for any real-world applications that may face. We're also in the process of patents and publishing, so we want to initiate the process of publishing our paper to share our findings and protect our innovative design.
Go into lessons learned. So we encountered many issues with 3D printing, as Josh mentioned earlier. It was a little difficult trying to scale it down. Some of the parts broke, nozzles clogged, and just the scaling down was a difficult part of the process. Ensuring the consistent communication between Fuquay, Zachary, as well as TxDOT. A lot of their information was proprietary, so we were kind of had to work with what we were given. and we made it do. Another big lesson we learned was designing to stress is not always the best option. Sometimes you must design towards displacement. Like Josh was mentioning earlier, we were focused on the rigidity of this rover. That way, when you have like a force on the end of that spray track and it's pushing down on it, you weren't getting an inconsistent spray because of the distance between the wall.
And then just our acknowledgements, we would like to thank our professor, Mr. Grady Eisensee, for his support and guidance through this whole project. Dr. Ben Way for his mentorship and his help with the control algorithm, as well as the special thanks to Texas Department of Transportation for their inspiration on this project, as well as Fuquay and Zachary for their helpful insight. Oh, and here are references and then any questions.
We'll take questions from the judges first, and then we'll take any from the audience, and we'll go till about 10:27. Any questions from the judges?
Question, when y'all were looking at the spray from the nozzle, was there any consideration about how much spray was coming out of the nozzle and any reactive forces on your machine and what that might do to your design?
Yes, actually, so polyurethane itself is very dense, and so it takes a lot of power to spray it. As you can see, it's a two-part spray, actually. The part A is 800 to 1100 PSI, part B is 1200 to 1500 PSI, and Josh, we were actually able to design that spray track and that nozzle in order to consider those forces at the ends. So that's why we were saying that we were trying to design the rover based off of displacement and not just on stress. Because when you have that nozzle on that far end and you have that large force, it'll tend to want to do this. And that separates it from the wall a little bit, and you can get an inconsistent spray. So we were trying to design it more towards rigidity, so we didn't have that issue.
I'd like to add one thing. We did do those calculations and we were looking at about a 2 to 5 pound pushback, and we did consider that. Because it is thick, but it's actually a very low amount of volume that comes out at once. So you don't have as much pushback as say like a pressure washer.
It's a pretty good mist. Like,
Thank you.
good question.
Great job.
How many different configurations of culverts did you consider when you evidently have a different program for each one? How do you acclimate the rover to different configurations?
We did have a constraint, I believe, that it can only go up to 11 feet.
4x4 to 11.
4x4 to 11x11.
Yeah, there are sensors on there that would detect the wall distances and maintain the spray nozzle that's 10 inches off the wall as it goes around the wall. So that would be included in
No,
the
that's
guesses.
And I noted in your earlier views that when there was a man with a spray gun in his hand, he was all covered up.
Yes.
I assume he was covered up because he was getting back spray or.
Yeah,
coming
just-
off.
yeah.
What do you think that rover's gonna look like a year in?
That is something we considered. That's one of the reasons why we chose to do an aluminum that has a bit of abrasion resistance even on our arms, so you can scrape off that excess buildup over time, or as through its normal operation. As part of the standard operating procedures, you would clean the rover after you're done using it to try to prevent buildup of that.
We also designed that large base that kind of revolves like an excavator. We designed it to kind of encompass so that there wasn't a lot that came into the track area. So it's kind of like a splash guard.
Also, the way it travels is that spraying this way and it's moving this
Yeah,
way.
right,
So it's never
right.
going to really,
So we're
Yeah.
actually spraying behind us. So we drive the rover in, the arm comes out in front of it, comes up, and then it sprays back like this. So, but there are still some spray back if there's wind, of course. And we did take that into consideration.
You indicate, my last question perhaps is, you indicated that it was made out of metal or some statement like that, and it wasn't gonna break down, or that was what I got out of it.
yes, sir.
You didn't use those words, but I'm gonna propose it is gonna break down.
Yes, sir. Yes, sir.
And it's gonna be in the middle of a culvert.
Yes, sir.
The culverts are how long?
No.
They
Get to 400
They
feet.
can be up to 400.
That's just,
And now the culvert's a fairly tight, rover's a fairly tight fit in the culvert. right?
Yes, sir.
Now we got 4 people lifting 45 pounds and they're not standing up,
no.
right?
Yes, sir.
Kind of touch down in any position. Is there Is there sensitivity to having the unit freewheeled some way to where you can make it roll easy?
We do have lifting lugs on the side of the
Yeah,
support roller.
and like
Yeah.
if it's in confined
Oh,
space. Yeah,
Yeah.
freewheeling it would be a good idea.
That'd be
I
one
don't
of the
think we,
features that we probably.
Yeah,
Yeah,
I
we
understand.
didn't-
We
we
considered
didn't-
adding.
right.
I was gonna say, we just like tether it and just pull it back.
Yeah,
Sell it with the trailer with a winch on it, hook up your.
Yeah,
yeah, right.
Yeah.
No, we definitely discussed that at one point in time.
Yeah, we did discuss putting like a tow anchor on the back of it. So you could, like you said, hook it up to a winch and pull it back if it did break down in there. But that would have to be if it was freewheeled, which that would have to have another section of design that we didn't quite go into, but that's a good question, good point.
Did you consider any other type of motors besides electric motors?
We primarily wanted to stick with the electrics, just because it's a lot smaller of wires that we have to run to the rover. And we have to run through the arm, so if we try to do stuff like hydraulics, there's a lot larger hoses. Of course, weight does become a little bit less of a factor at that point. But then the arms themselves would have to be scaled up quite a bit more. And then that could start impacting our ability to go in there. And then also using the other review steppers is because they have high positional accuracy. The only other motors that could have something similar to that would be like servo motors. And those motors they're not as built for holding torques and holding specs. Whereas with the reason we went with steppers, because the arm is going to sit in the position while the track sprays, it's going to have very small incremental movements. So it's doing more holding than it is moving at that point.
Any
I
other-
want to move to an industrial question here. I noticed in your earliest photos, you showed quite a bit of residue, I'll call it dried mud.
Yeah,
Oh, yeah, here.
yes.
I assume that dried mud's got to come out of there first, is we're gonna put.
Yes,
polyurethane
so,
on bottom.
Part of the inspiration was, so I used to have an internship at TechStar Enterprise. While we were there, they actually had a rover that was made to specifically take all of that mud and debris out. So after that process was done, then it was power washed, and after it was power washed and dried, that's when they would apply the polyurethane liner by hand. So that's kind of where, like, why can't we have a rover to apply this application for this maintenance issue? So that's kind of where inspiration came out. So yes, they did have to take all of that out, and they had a lot of specifications for that as well. So
We considered actually having a rover that does the power washing, the etching of the sides, as well as the polyurethane
yes,
application, but that was just a really, really big project. Like that would have taken a while. So we just stuck with the polyurethane application.
Any last quick questions? Like, quick comment there, you said you want to increase your efficiency by 100%. And that was in your objectives, but you never defined what your efficiency was and.
So currently,
I'm just addressing because I don't,
Yeah.
I want to see if there's any other.
That was his question,
My
actually.
question was
Yeah.
actually gonna be on that. You define your efficiency as wanting to increase it 100%. I think you said you want to increase like variance and coverage by 6 or inconsistency by 60%, labor cost by 70%, which is great. You also said you needed 4 personnel to lift the rover. There's obviously some kind of control mechanism in there. So I guess what metrics are you using to define your increase in efficiency? What kind of measurements are you taking to quantify your inconsistency in your application? Your code?
so for the
Well,
efficiency.
1 minute response.
Okay.
okay.
Yeah, so for the efficiency, 'cause that's probably gonna be the biggest one. In a 24-hour period, they can only spend approximately 4 hours actually applying the application in the culvert. Because especially down here in Texas, they can only work at 15-minute stints due to OSHA requirements. So that is where we'd be, at least in an 8-hour period, we would be able to spray continuously in that entire 8 hours. So that's where we're doubling our efficiency, hence the 100%. That's how that went through.
Thanks. We got to cut you off
All right.
here.